for today's seminar, general seminar. I would like an applause to welcome Franck Plouraboué. Franck Plouraboué that I met during my postdoc in Toulouse. We've been working with plasma, with cold plasma, plasma propulsion, motionless propulsion for aerospace applications. And while chit-chatting with Franck, once he told me, but you know, Francesco, don't you like this kind of stuff, a very low speed, low Reynolds number and stuff? Why? I've been working on that. I got a patent on that. Ah, yes. And another time, I got to his office saying, hey, Franck, what do you think about this? Hey, we got a paper on that. So the nice thing about Franck is that he will be presenting you something, but be sure that he's been working on something else. Now there's Stephanie that is coming by, and she met Franck this very morning in the corridor saying, ah, Franck, haven't you been working on crushed paper stuff like that? Yes, that was me. So Franck, it's like that. You always enjoy doing things that are completely different, but linked by asymptotic analysis, because there will be always some asymptotic analysis inside.
I don't know.
Maybe, we don't know. So we welcome Franck again, and it's up to you.
Thank you. Thank you very much. I'm very pleased to be here today and following the invitation of Francesco and Pierre-Yves. And it's great not to be in D'Alembert again. So I did a seminar like a long time ago, and I'm very happy to be here today. So today I will present a journey. That's maybe a choice. And in a journey you have stages, and in those stages generally you are quite superficial in what you see. So it's the choice of this seminar having like 5 topics, and each of those will be like a little superficial, so I apologize in advance for that. But I hope I will give a broad overview of the topic before, because also Francesco told me that I should present for a broad audience and the first things for students. So I'm starting with lecturing, the first 2-3 slides, and then I will start over on the topic, right? So this is a journey on wave propagations through networks. So first, the point is that, I already gave the context, waves are interested because there are non-destructive testing tools for non-intrusive detections, and this is used for pipes for having an idea about their long-term behavior and how they are perhaps modified by oxidations, reactions occurring into those blockages, whatever. And that's why waves are already interesting in pipe systems. So in this context, there is what is called waveguides, acoustic propagations into long structures. And here the structures can be having a section omega orthogonal, which is a transverse section of the tube, to say. And on those structures, you are looking at the wave propagation. That's the wave operator, the D'Alembert operator. That's why I thought also this talk was nice for being in D'Alembert. And you split the Laplacian into the transverse part and the longitudinal part. And then you are looking for solutions where you have, again, eigen functions which depends on the transverse direction x orthogonal and have a given frequency with an exponential variation in the z longitudinal direction, okay? That's the standard way to procedure to study the wave propagation in waveguides. So then, if you insert this into the wave propagation, you end up with a Helmholtz problem, where you have a transverse Laplacian acting onto a constant, plus a constant acting onto the eigenmodes. And this constant is a kind of eigenvalue for the transverse operator. And besides the fact that you are looking for Neumann conditions for this potential, this sets a problem where you have all the good properties, that this is a self-adjoint operator, and for that you know that you have a discrete sets of eigenvalues, and those eigenvalues you can rank them into the first one, which is 0 for the Neumann problems, and other ones which are non-zero. Okay, that's the standard procedure to study waveguides. So that's the lecturing part. Then those wave eigenvalues, you can have them having this property that the frequency is larger than the eigenvalue, that will send propagative modes. This frequency should be smaller than this eigenvalue. Then you will have Evanescent modes, that is to say modes that are going to decay along Z in one direction or the other. And you have this very special case where this eigenvalue is 0. That's the first mode, okay? In that case, you have this relationship between the frequency and the wavelengths, and this is a plane wave. So if you look at the possible velocities of those waves, the plane waves is the following. It's the red one here. It does not depend on the frequency. It's a non-dispersive wave. Whereas the other ones, which are evanescent waves, they do depend on omega, and so you see the velocity depends on the frequency. Another thing is that those evanescent waves, there are an infinite set of those. So a given frequency here, you have an infinite sets of possible evanescent waves, and they're always there. So that's waveguides, and most of what I'm going to talk today would be plane waves. So I'm going to more or less ignore the influence of those other waves, but at the end of the talk, I will talk about the interactions between evanescent waves and plane waves. That's what I'm going to talk. So now the point is that in this plane wave acoustic guides framework, you see that every mode depends on the frequency, but all possible frequencies are continuously possible. Okay, this is not the case if you look at a system where you have boundary conditions. So now, if you have a pipe with a given pressure applied at one end, and something here which is a valve which can open, then this valve will set a boundary condition. So now I'm looking at a dimensionless version of this, where the time scales is defined as an advective time scale, for which that's the time for the wave to go from one end to the other one. The longitudinal length scale is obviously non-dimensionalized by the size of the system, so that you have 0 there and 1 here for Z, the non-dimensional variable. You have the one-dimensional D'Alembert operator acting on the dimensionless operator acting on the pressure. And on one hand, you set up a constant pressure, which is defined as the reference pressure of the reservoir, which is there. And on the other hand, you apply a boundary condition, which is hereby the impulse solution for this problem, where you set up a Dirac for the flux, which, because the longitudinal pressure gradient is nothing else in dimensionless unit as a velocity. Okay, so opening the valve is in fact opening the velocity for the flow, and this is a sudden acceleration. That's why you have this Dirac there. So you can find an analytic solution for this problem. One bit of this analytic solution is there, which is in fact Z, which is in the kernel of the Laplacian operator, and the Dirac, which is there, so that you see that this particular solution is going to take care of the non-homogeneous boundary condition that we have here. Okay, that's this particular solution for this boundary condition. And this other bit here is related to what is called the homogeneous problem, that is to say when the boundary condition will be 0 there. Okay, this homogeneous part is in fact a series involving eigenfunctions, which are these bits here, and they do depend on lambda, which is a set of discrete eigenvalues. And this time, the eigenvalues are going to be set by the boundary condition that we apply here, which is a homogeneous boundary condition related to the derivative in Z. So this sign becomes a cosine, and then this cosine being 0 leaves discrete eigenvalues being these ones. Right. So that's a very simple problem for students, okay? But the interesting thing here is that, in fact, the boundary conditions, they drive a discrete spectrum. Okay, and that's really the key physical issue here. And then the question is, okay, what happens on networks? Do we have eigenvalues, and what sets the eigenvalues of the problems? Okay, that's something I'm going to answer in the talk. And for notation simplification, I will quote this lambda 0k, which was, you remember, the eigenvalue of the plane wave. I will call them lambda k, because we will mainly deal with plane waves, okay? But at the end, I also mentioned the fact that I will talk about the interaction between these plane waves and the evanescent waves. Right, so now a little vocabulary. I will also, rather than specifically talk about a given set of boundary conditions, I will talk about this eigenvalue decomposition of the homogeneous solution, and I will call them psi of lambda k, those signs. So those sign of lambda k, you see, these are those sign functions. They are, let's say, the prefactor there is meant to make them orthogonal. So they are orthogonal, and you have this orthogonality relationship between the eigenvalues, the eigenfunctions, sorry. Right. So now I'm going to talk about networks. Well, why networks are interesting? So they're interesting in various contexts. For example, in water distribution networks, where you have an example here. But other ones, like, for example, vascular networks. Or trees, possibly. But also in solids, because not only you can have waves driven by pressure into those pipes networks, but you can also have compressive or shear waves into structured systems like beam scaffoldings, and maybe other ones in solids. But the problem is now to go from networks to what is called a metric graph. So that's an illustration. Here, this is a network of arteries, which is behind the cerebral system. And I now have to say some words about what is called a metric graph. So everybody knows what is a graph. So this is an example of a graph which has nodes and edges. But you also know that a graph is only related to the topology of the connections between those entities, right? So if you deform this graph and you make this node here, you displace it, and you change the length between V5 and V8, this is the same graph, obviously, okay? But this is not the case for a metric graph. So a metric graph is a graph where the edge between two nodes has a given length, and this length is specified. Okay, so that makes a metric graph an object which, in fact, depends on the size. For geometric graph, size matter. So the advantage or the interest of a metric graph is that then you have a length, you have a physical length between the entities, and this provides the opportunity to define new mathematical objects onto this metric graph, and for example, functions defined onto this. So functions, and if you have functions, then you can have operator acting on these functions. And those operators are the things I'm going to be interested in, right? So they are called quantum graph in the vocabulary of mathematical physics, and this comes from quantum mechanics. I'm not going to give a lot of details about the origin of this denomination, but I will give some elements about why this is an interesting object and why it does provide interesting things. Okay, so then the question is, these real networks, can we idealize them as a metric graph? Some of them, yes, but rapidly you're going to see that, real networks are complex, possibly, even more complex than that, because you have what I call singularities, where you have sudden change in sections in short distances. So this happens also in biology, for example, in physiology, where in the brains you have some vessels that deform, and they manage to make some pathological systems called aneurysms. And then the question is, when you have a complex network with some curve changes and possibly localized change in diameters, how can we map them into metric graphs? And I will give a words on the last section of the talk, saying that, okay, there are two deep possibilities where we can change or replace singularity by an impedance matrix, or possibly change boundary conditions. And I will talk about that. Okay, so I think I'm done with the introduction. No, not yet, because I've said words about acoustic propagation into complex structures, why graphs are interesting, and now I'm going to give some words about water hammer. So in the audience, maybe some of you knows, but maybe some don't. So water hammer is a wave which is generated when in a system of pipe you suddenly interrupt the flux, or you open the flux. So it happens in your bathroom if you open the tube, then you can hear, if you open suddenly, boom, something which is related to this wave. So one very important relation in this water hammer context is the Joukowsky relation, and this Joukowsky provides you what is the amplitude of the pressure drop provided by this wave. How is it related to the change in the flux that you have? In fact, it does not depend on the flux, it depends on the velocity. That is to say, the change in velocity that you have in the tube, right? So imagine that you are opening this valve there. If you open it, that's the change in velocity delta W that will make this pressure here, which is a kind of mixed Bernoulli, because it's rho, the fluid density, multiplied by two velocities. One which is the change in velocity due to the change in the opening that you've done, and this Cp, which is in fact the velocity of the wave. And it turns out that this Cp here, I'm not going to give details, but this Cp is very large. For, let's say, a liquid like water into a steel pipe, a pipe in metallic, this Cp is close to 10 to the 3. So 10 to the 3 meter per second. So it's 1,000 meters per second is very fast, okay? And since rho f is also 10 to the 3, it leaves you that if you have a change in velocity which is, let's say, 0.1 meter per second, the pressure drive that you will get from the wave would be close to 1 atmosphere, which is already large, okay? But if you have, let's say, 10 meters per second there, or 1 meter per second there, you will have 10 atmospheres, which is huge and is going to damage the system, okay? And that's why the water hammer is so important in hydraulic, because a lot of damage events have been realized in the past in many installations, and that's why in engineering this is a big issue. Okay, so now that I said that, you're going to see an illustration of a water hammer propagating into the system, which is a glass where you can see the wave appearing. And the wave is going to bump from here to there. It changes sign when it bumps, but also you will see that it will displace the whole system, because there is a coupling between the pressure and the deformation of the total system. And that's coupling is called free structure interaction. So it can happen in real installations, and as you've seen here, it is a Toulouse picture where it happens near Place du Capitole. And because this is a high pressure systems, you see that you have like 20 meters height water flowing, because it's high pressurized water delivery, okay? So from that you understand the important applicative issue related to that wave. And another illustration is provided here, where you see here the entire network, water distribution network of Toulouse town, here, detail, where you see in green dots, where the pressure is recorded at some location, and you see here the pressure variations associated with one event arising at one of those points. And from what you can see here, that the synchronization of the event arising in each detector is very close because, as I said, the velocity was very fast. So there is a little time between the wave arriving at one or the other, okay? But what you can see also is that the time length of these waves could be like a minute or something like that. So it's not decaying slowly. So the waves, since it takes like 1 second to go from one position in town to another one, in like 30 seconds it bumps like 30 times all around in the town. So when this kind of event happens somewhere, it bumps all over the place in a myriad of reverberations of the wave. And that's why these kind of events are quite damaging, because it goes everywhere. So the motivation for this recording here in this paper was to define a way, an algorithm by which, if you record at some places, you can, let's say, approximate the region where the events occur. That is to say, where was the origin of the whole wave. So we set up a triangulation method to make an approximation of the origin, and which is derived here in various colors, yellow, orange, and red, for the most probable place. And it turns out that in that case we have been able to recover the fact that it was a pump of one of the hydraulic system of the town, which was responsible for this, and that we predicted correctly. Okay, but that is not really something I'm going to talk today. It was just an illustration of the interest of water-hammer wave propagation into networks. Right, so from that, now I'm going to survey a little more in detail the literature on the topic. So one very nice paper about this problem is this Iris Tischling review on the fluid structure interaction modeling of water-hammer, and I will detail that on the topic. Here are some other papers related to the wave propagation, but all those papers have ignored the fluid interactions, and that's why I'm going to talk about fluid interaction later on. We have added some papers, and I will mention them at the end of the talk. But the most interesting, I guess, point here is that I've written a review paper on that. And if you're interested in water-hammer, I suggest you to read this paper, because it's quite complete over the last 15 years of research on the topic. Right. Okay, so these water-hammer waves, let's say, in this literature, people talk about couplings associated with those waves. So the first coupling is related to the fact that you have junctions between pipes, and there are relations between those junctions. And because the wave, when it propagates from one junction to another one, it needs to share information at the edges, at the articulations between those functions. And these connections between the pipes, they are called junction couplings. So this is a way of describing the fact that you need boundary conditions to be applied between the waves arising in the various pipes. And so we already have an example of this for a single pipe where you have a valve at the end. Then at this location of the valve, we had a boundary condition. Okay, but this is a more general way of talking about the fact that you have connections and then boundary conditions in between those pipes. There is another coupling which is called friction coupling, and this is related to the wave damping. So the mechanism of the wave damping could be bulk fluid attenuation, but it turns out that if you look at the numbers, the water attenuation factor is around 10 to the minus 7 f squared, where f is the frequency of the wave in kilohertz. So if you look at frequencies close to, let's say, 1 kilohertz, you need 10 to the 7 meter for the wave to attenuate. That is to say, more than 10 kilometers. So in fact, this wave attenuation is well less than another mechanism, which is the boundary layer attenuation. The attenuation of the waves nearby the boundary layers. And I will emphasize that and discuss about the modeling of the boundary layer attenuation for the wave. And the last coupling is called the Poisson coupling, which is in fact related to the free structure interaction, and I will talk about that also. Okay, so I've more or less ended the survey part. I'm going to talk about more specifically some contribution that we did on this subject. So the first thing I'm going to talk is waves without free structure interaction and without friction coupling, but with junction couplings at the edge on the network. So let's consider a very simple example of a metric graph, which is this 3-star graph, where 2 is the vertex where some boundary condition is going to apply. That's why it is in red. And this is the adjacency matrix of this graph there, which is really simple, okay? Then on this graph, we want to consider the propagation of the waves. And for that, we are going to consider those eigenfunctions here, which are the eigenfunctions of the Laplacian operator acting on the graph. So that is to say, functions which are defined everywhere, which are continuous, that will be continuous function all along, okay? And moreover, those functions, they will fulfill some condition on each vertex, which is can be written this way, where A is the adjacency matrix, and d by dz is the derivative of the eigenfunction, and hi is a kind of constant which is defined at every location, at every vertex, so that this is a kind of generalization of Kirchhoff law. Okay, it looks like a Kirchhoff-Robin for people used for this kind of condition, or Kirchhoff-Fourier for thermal people, okay, whatever. That's a mixed Dirichlet-Neumann at the edge. That's the most general linear boundary condition you can think about. And when this H is non-zero, it's related, because it is in red there, it's related to the fact that in fact this is at only this node where you apply something which is non-homogeneous. So you change something at this node, and then only this Hi for H2 will be non-zero, and all the other ones will be zero, okay? So it means that the boundary condition also can be looked at, the previous slide here. This can be written exactly the same way, but a little different, as a sum of the flux. So acoustical people are more used with this wording there, where if you look at that being zero, that's the boundary condition is just the conservation of the acoustic flux perturbation, okay? So this acoustic flux perturbation can be written also as a product between the surface, the local section of the pipes, multiplied by the pressure gradient, okay? If it is non-homogeneous, let us say for example in the 2, there is a right-hand side, and this right-hand side is related to a given function of time, but located at the vertex, which is the vertex number 2. And so this non-homogeneous boundary condition applied at some point can be handled with a particular solution, what was called PP, and this particular solution is going to, in fact, handle this by a classical Fourier decomposition, okay? And the other one here, it's the homogeneous parts, it then decompose into the quantum graph eigenfunctions, psi. So those quantum graph eigenfunctions are these ones in black, where this right-hand side is zero, where there is a Kirchhoff boundary condition applied. Then, okay, that's a formal solution for the problem. We can be more specific, we can find this and that. And to find that, in fact, it's possible to do it recalling the modal decomposition just written. And because the psi ij, which are the eigenfunction, they can be explicitly written because they are the simple eigenfunction of the one-dimensional Laplacian. So they can be written as sine functions this way. And the nice way of writing them, so ij means the edge linking the vertex I to the vertex j. Okay, so this ij there provides you the functions along this edge there for tree 1, for example, for tree 2. And this eigenfunction is related to phi I, phi j, which are in fact the value of the pressure at each vertex. Okay, so if you take z equal to 0 there, these terms cancels. This one is just phi I sine lambda L I j, which simplifies with that. And since this edge has a IAG equal to 1, it means that this is equal to phi I. Okay, the same applies for phi j. So this is bulked so that in fact it's equal to phi I in vertex I, phi j in vertex j, and so it's continuous, and it's the solution of that, right? So then you realize that the boundary condition applied at each vertex can be set as a linear system acting on the phi, this scalar. So this in fact is a vector, and you can build this boundary condition there as a linear operator acting on that. And because it's equal to 0, then you have two possibilities. Either every phi I is 0, which is fine, but this is boring, okay? Or something else interesting happens if this matrix here has a non-empty kernel. Okay, non-empty kernels means that it could arise that for non-zero phi I. Okay, so this non-empty kernel, this condition, is equal to say that this matrix, the matrix that you can build, and in fact, you can build this matrix, okay? That's the formula for this matrix. This matrix, by the way, is called a secular matrix. Okay, this matrix, the condition that you have is the determinant of this matrix equal to 0. That's the non-empty kernel condition that you get. And that permits to define you the eigenfunctions, the eigenvalues, these lambdas, from this condition. So these conditions provide you the discrete spectrum I mentioned at the beginning of the talk, but for networks, okay? So this is kind of more or less new in the domain. What is more or less known, sorry, in the domain. What is new is this how to decompose a solution into particular and general. That's something new and detailed in this paper. So now that I've said that, I can show you some illustration on this three-star graph. We can, in that case, compute explicitly the determinant of this secular matrix. This is this formula. And we can plot, we can compute the lambdas from zeros of this determinant. So you see that you have to solve a transcendent equation, okay? But it's easy, it's a 1D problem. And also you know where are the zeros, well, you know the ranges where are the zeros, so you can have a very simple solver for one-dimensional problem. And it's also easy to parallelize if you need. So that's a nice way of dealing with this spectrum, discrete spectrum computation. And this is the leading order mode here. That's the second one that you get. Okay, that's an illustration. So now I'm going to talk about how to include viscous dissipation into this framework. That will be with the friction coupling, okay? But for that, I need to step back and discuss about how can you done that in a very simple example. So I'm going to go back to this pipe problem there. It was already non-dimensional, but I will going to add some bits on it. And the first bit I'm going to add is to define what is called the water hammer dimensionless parameter, which is called delta. This water hammer parameter is in fact very simple. That's the ratio between two time scale. The advective time scale, the time for the waves to go from one end to the other one, and a diffusive time scale. And this diffusive time scale is obviously S square over nu. Okay, so you recognize here S square over nu, the diffusive time scale, on the numerator and on the denominator, and on the numerator you have L over Cp. Okay, so it turns out this small parameter is in front of the right-hand side here, which is related to this, which is the gradient of the wall shear stress. So this is known. This is in fact related to the effect of the boundary layer onto the pressure propagation into pipe. That's classical, okay? And this is more or less the same problem as previously, where we apply Dirac on the right, on z equal 1 for the velocity. So in that case, there is a paper by C.C. May and Jing in 2016 where they solved this problem using a multi-time scale analysis. And that's something I'm going to detail here in order to show you what are the features and how this can be understood. So the main motivation for that, in fact, is to find when you have a signal where the wave is bouncing back and forth into the pipe system, where you have those waves going up and down here, because this is a recording of the pressure in one location. So when the wave goes back and forth, you have this up and down for the pressure. So it goes fast, but there is an envelope of this wave, and this envelope has a slow time scale decay. So the motivation for this theory is to find what is this envelope time scales, and can we compute them? So to do that, you use the fact that this right-hand side here is small, because there is a small parameter into it. So you search for solutions which are asymptotic solutions in delta, and you set up a multi-time scale decomposition where you have a fast time scale tau and low time scale capital T. Okay? And the time derivative is in fact the composition of those two, where the slow time scales obviously has a small parameter in front of it. Right? So you decompose this time scale operator, which is there, into tau for the leading order. And at the next order, you have this term here, which is a mixed, a low time scale, small time scale, acting on the leading order pressure, right? So you have this term. But you also have the right-hand side contribution of the Walshy stress. So the steps are going to say, okay, I'm going to solve for the leading order. Hopefully I will be able to compute it. And then after that, I will need first to compute the Walshy stress to get the right-hand side, then the leading order to have this term, and I will be maybe able to compute the first order. The point is that here, in fact, the first order is not very much the issue that we would like to understand. The main issue is that we would like to understand what is the low time scale variation of the leading order. So from that step to this step, in fact, what we are going to say to set is that we are going to say that, in fact, when it enters into this first order, the leading order will have a low time scale envelope that we will wish to understand and to find. Okay? I'm going to make some details about that. So let us start with the leading order. That's the leading order. As previously, it has a particular solution associated with the boundary condition and homogeneous part, which is decomposed into eigenfunctions, psi of lambda k. You see that this leading order here, the non-homogeneous part, is in fact z multiplied by the Dirac in time. Dirac in time, you go into the Laplace transformation of that. It's a 1, it's a constant. Then you have this term there, which is z. You project this z onto the psi lambda k, which is a eigenfunction base, orthogonal base, and then you can easily find A0 from the projection onto the eigenfunction, and that will give you explicitly the A0, the amplitude of the leading order mode, onto each eigenfunction. A projection of the particular solution into each eigenfunction. Okay, so you have A in the Laplace domain. That's good, that's fine. And then you need to solve for the Walshy stress. So to address the Walshy stress, you need to solve what is called the boundary layer problem for the longitudinal velocity W. So that's that's come from the Navier-Stokes equation. You have this boundary layer problem where the longitudinal diffusion equation for the momentum diffusion is forced by the longitudinal pressure gradient. You can set that into the Laplace domain, and you can solve that immediately in the Laplace domain this way. So it's an easy solution that you can get. And from this W, you can compute the wall shear stress, which is the derivative of this velocity, leading order velocity gradient, radial gradient, the gradient orthogonal to the longitudinal direction. Applied it at y is equal to 0, which is at the wall, and you find that, in fact, this simple formula, the wall shear stress, is related to the pressure gradient up to some S value parameter in the Laplace domain. Then you can replace that formula into here. If you derive on Z, what is going to be derived is the pressure, okay? And then you can then plug the leading order in here, but the new thing here is that now when you look at the first order, you add the fact that, in fact, the leading order has a possible amplitude here, which is the envelope, a low time scale envelope. And then in here, you have this derivative in capital T, which we're going to act onto this envelope there. So you can make this computation. So decompose P1 into the same base as P0, project onto the, again, modes C lambda K. And what you end up with is that you have a given operator acting on A0, that's the envelope of the leading order. And this operator here will be possibly non-zero, okay? So if you find those two amplitudes for the leading order, what you want to set is that you don't want this P1 to become infinite at finite time. Because you want, this is a kind of consistency condition for the asymptotic multi-time scale analysis that you are doing, okay? So if you set that, if you said, okay, the leading order, the first order correction in time should not diverge, it's the same as setting that there is no double pole in the Laplace domain. So maybe I will have the opportunity at the end of the talk, if you have questions, to say you why, but it's a kind of one-to-one mapping. No divergence in time equals no double pole in Laplace domain. So there is an easy deduction from that. The deduction is that you kill the double poles means you won't have these divergent terms. So that condition is called a secularity condition. That's in the multi-time scale approach. That's how it happens. Okay. So you set the secularity conditions means that you cancel the double poles. So if you do that, you see that in fact here you have one pole because this product is lambda k minus is multiplied by lambda k plus is. So there is one single pole, and then there is another one there. So these will make two double poles from these two terms. So you need to kill all those terms there. So it ends up with saying that this has to be 0. So if you do that, you end up with that condition because this is easy to integrate. It gives you an exponential, right? And an exponential of racine square root of s, evaluated as s goes to plus minus I lambda k. And this gives you this exponential way of the amplitude envelopes goes depending on the eigenvalue, lambda k. So you see that because of the square root of I, the imaginary I unit, you have one piece of the term here which will have a decaying exponential amplitude by the minus 1/2 of this, okay? And you will have also a phase change at low time scale. So if you plug that into the solution we previously had, what is going to change is going to change the amplitude there, which is going to be exponentially decaying, and also the phase into the sinus, which is going to be slightly changed by the low time scale. So that's an explicit solution for this slow time scale analysis, and that gives you what should happen, depending on the eigenvalues of the problem. So that's the May paper, in kind of reshaped by this Laplace formulation, which shortcuts a lot the computations from the original paper. So this is already a shortcut. So the nice thing is that what you find is that the eigenvalues not only gives you the main modes, but they also gives you what is going to be the damping. And that's the main issue, right? And all these steps can be applied into networks. And that's one I'm now going to present. Oh, by the way, this is the comparison between this theory and various experiments into a single pipe, where this theory is in dot, these ones, and the experiments are other symbols. So you see that it's not a perfectly matching theory, but it's already give you a nice what is what?
There's a dotted line and
Yes, I didn't. So I was expecting the question. Thank you. So the other one will be the next theory I'm going to present later. Okay, that's with the free structure interaction. So let's go back to networks. Then we do exactly the same thing, but now we are dealing with a pressure which is defined onto the metric graph. So that's this symbol there means a function defined over all the graph lengths, edges, continuous at every vertex. And you do the same expansion in small time scale delta Waterhammer parameter. And if you do that, then you will end up with this decomposition into these sets of eigenfunctions which are homogeneous, and this set of eigenfunctions which are dealing with, in fact, the particular solution associated with the boundary condition applied at one node. Okay? In both cases, they have both amplitudes, the homogeneous one here and the non-homogeneous one there, but you can do the same steps, decomposing the first order, then you have this operator acting on the first order. It's a little more, let's say, algebra, but it's not that complex. And you end up when, in fact, you can divide the double poles, because you see that this term there is one pole there, and there is another pole there. And you see that, in fact, here there are two poles, possibly. So there will be a double pole there and double pole there. So there will be two conditions, this one and that one. And as previously, you can integrate that condition immediately, find that it's, in fact, related to the eigenvalues, this eigenvalue for the homogeneous problem, this eigenvalue for the particular problem, and find explicitly the solution with this mode amplitude there, the phase which is here, which is a long time scale phase, etc. So that's the very interesting part here, is that in fact in networks this result goes generally as the fact that we know that the discrete spectrum given by the circularity matrix not only gives you the modes, but also the way they will be damped by viscous boundary layers, which is a very nice result related to this May and June analysis onto graphs, metric graphs. Okay, so now I'm going to talk about free structure interaction. That's the part I was mentioning before. So for that, I'm sorry that I need to give you these Tischling four-couple FSI equations, which are coming from 1996. It's a long time ago already, because it was the year I had my PhD, so a long time ago. And so this author there derived these sets of equations which are related to four quantities. Pressure, we already saw that. W, which is the velocity in the pipe, okay? Sigma ZZ, which is the longitudinal part of the stress tensor into the wall, and zeta dot here, which is the velocity of the deformation along the Z direction. Okay, that's the four entities related to that wave. And you see that it's written as a first order hyperbolic problem in time and space. Okay, It's coupled because those matrices here are not that, there are non-diagonal terms. And there is a right-hand side. So it looks a little complicated, and also Tischling provide what is the wave velocity depending on the parameters, because this is something I didn't mention previously. This velocity was given, but I didn't say how, was related to parameters. So Tischling this very nice formula there. In fact, it turns out that this formula works very well. And we have to wait 1996 for having the right formula, because in that area of water hammer, people a lot of time propose various laws for these velocities, and so it's a long history on this, but I'm not going to talk about that. Okay, so this is a little complicated on one hand because there are 4 quantities, there are coupled, okay, but it's written this way because Tischling and Mimi authors in the area, they were focused into finding numerical solutions for this kind of problem, and when you are looking at numerical solution, what you want is a parameter of lowest order, because you don't have numerical diffusion coming from hyperbolic terms and so on and so on, okay? But what we wanted to do was analytical solutions, for which, in fact, it turns out that it's more easier to write all this as a wave operator, both in second order in time and space, acting on a vector P, which is in fact a 2-component vector, pressure and longitudinal stress only. And you can show that there is a one-to-one mapping between those formulations. But in here, in fact, what you have is a couple waves, because this CP here is a matrix, and this matrix has non-diagonal terms. Okay? So if nu S, which is the Poisson parameter for the solid, is 0, then there is no coupling. In fact, you have 2 waves propagating independently the pressure and the stress wave. So the physics about that is obvious. I mean, there is elastic waves propagating into the solid because you deform it. So those elastic waves are living their life, okay? And you have the pressure wave I already mentioned, okay? And obviously they have different distinct velocities because they don't propagate the same velocity, okay? And now it's interesting to see that in fact you have Poisson coupling because it's related to the Poisson coefficient there. Because it's related to the fact that the deformation in radial direction is in fact related to the deformation along the longitudinal direction from the Poisson coupling. That's how the coupling arises. Okay, so many people in the water hammer, when they lead to waves into networks, they ignore this effect. But it turns out that this effect might be important or interesting, and that's why we're interested in. So obviously there is a right-hand side related to that. It can be written in the dimensionless formulation related to the water hammer parameter I just mentioned previously. But in the first part, I'm going to ignore that this time, because I'm dealing with the free structure interaction. Okay, then the classical way to solve this kind of coupled problem is obviously to go into the orthogonal base of this matrix. Because in that, so we call italic, say, this C, which has a curve shape rather than these ones, to talk about the diagonal base of this matrix C, okay? And in this base, we call them velocity C minus and C plus to distinguish those, okay? So if we go into that space, then we need to change the unknown P. We have to apply the matrix pi onto P, and then we will have 2 diagonal problems, decoupled ones. So obviously, it's always like that. When you solve one problem, you have another one. You cannot put everything on the carpet because it's coupled. I mean, so this way is a way to decouple for sure, but then you will have couple elsewhere, and the coupling is going to arise at the boundary conditions. Okay, so I'm not taking that in all details, but the nice thing here that the propagating problem is in fact a copy of the previous one, more complex, but it's still decoupled. And that's the main issue, because you can write down the pressure problem as a eigenfunction decomposition as we did, because these eigenfunction compositions are now the eigenbase of this, let's say, twice Laplacian problem. That is to say, there is a diagonal operator acting on the derivative, but it doesn't change anything on the fact that you can handle still psi analytically, and it's easy to compute. Okay. So I'm not going to detail the boundary conditions, but now, as I said, there are a couple. Yeah. Okay, I'm going to try to be short. Thank you. So this is an example of the analytical solution in blue, compared with some numerical solutions in black. And you see that, in fact, we have a very good superposition for all the parameters given. So that's a nice, let's say, confirmation of this analytical solution is nice. And then I'm going to show what is going to happen on the solution. That's an example. So you see here, nu is 0, 0, 2, 0, 4. In all that column, we have P on the upper part, sigma ZZ on the other one. And you see that, in fact, as the pressure goes, here there is no coupling between pressure and stress, though there is no stress. But there is some coupling. And as the waves bumps back and forth, the pressure is handling more and more stress. And also you see that the stress velocity is faster than the pressure. So the pressure has high frequency coming from the coupling. Okay, that's why in the comparison that we had here, we had a lot of strangely high frequency events that look like noise, but they are not noise. They are coming from high frequency coupling between the twos. Okay, I'm going to skip that, which is the derivation of the Tischling equations from asymptotics. This is the comparison when we add some free structure interaction and some friction coupling into this free structure interaction theory. And you see that then we have a better comparison with the experiment. Okay, so now if we had friction coupling, you see that the envelope is going to decay, as I mentioned. And also that's more or less you see that there is some change in the stress. So if I want to go fast, maybe I need to skip this. I'm not going to talk about that. So that's what we can do if we add a free structure interaction into networks. So I'm skipping that. I'm going to talk directly on the last part of the talk, which is interaction between those plane waves and evanescent waves. So, okay, so now I'm going to try to see what would happen if I have a singularity. So let's say omega r is a singular domain shape connecting two tubes omega n minus omega n plus. And this singularity has a length which is d, so half length d over 2. It's symmetrical here from left to right, but it could be also symmetrical from top to bottom in that case. And this omega r is, in fact, here this singularity associated with a corner. Okay? And the question is, how will the plane wave be disturbed by this? So there is a nice paper by Martin, which did quite a lot of papers on that topic, but a recent one which is nice, which inspired a lot what is derived here, because we did further steps in its analysis. So it's a long wavelength analysis where we have a small parameter, which is the wavelength multiplied by R0, which is the radius of the pipe. And if in dimensionless unit, it's possible to see that this epsilon is related to epsilon 0, which is in fact the aspect ratio of the pipe, multiplied by the dimensionless frequency. So it's more or less a low frequency theory where this omega is order 1, if you say, for epsilon to be small compared to epsilon naught. And we want to in fact see what are the perturbations that's going to happen on the plane wave. So the plane wave is decomposed into an outer amplitude capital U and an inner one which is small u. And all those are going to change and interact together. And the point provided by Martin is that, in fact, he said that this outer can be decomposed into transmitted and reflected waves. And both the transmitted coefficient and the reflected coefficient can be decomposed into epsilon, having an asymptotic expansion in epsilon, right? So in the asymptotic expansion, R will have a rho n coefficients, and T will have tau n coefficients. And then the issue is that we need to know what are those coefficients in order to know what will be the perturbation onto the plane wave. Okay. So we can do the inner expansion in the same asymptotic parameters, and I'm give you the results. The inner expansion can be decomposed into a particular solution and a near-field solution. Here are the first 4 perturbations for the particular solution. They can be expanded in Z coefficients. We have closer problem associated with the near field. There are all harmonics problems which are more or less forced one together. And the beauty of this particular solution there is that, in fact, that's the solution with match with the outer region I already wrote. So this is a perfect matching, and it's absolutely analytical. So from that, you can find the alpha, the coefficients. I mentioned the alpha related to these coefficients of the transmitted and reflection waves. And we can have closed formulas for the alpha 1 and beta 1, depending on whatever geometry, which I've written here. You see here the boundary of omega r, and depending on polynomial expansion on Z acting on this geometry. So these are the first formula, but we can have a second one, the third ones, depending on the whole geometries. So it means that a given singularity, we can find explicitly what are the perturbation and transmission and the reflection waves. So then I will answer the fact that from that we can compute the transmission matrix, because we know that what is the matrix related to T and R. And okay, so I can build the transmission matrix. Okay, I'm not giving the details, but you have the main ideas. But also I can also write down this R and T as operator in time rather than in a Fourier space. And from that, we can have some kind of generalized, what's called Ingard-Meyers type of boundary conditions for singularities for liners in acoustic, for example. In that case, we have them at each orders in time. So that was I mentioned. You can also change the boundary condition if you have influence of the singularity. Okay, so my conclusions. We looked about spectrum and damping of long wavelengths plane waves into graphs and networks. I talked about Waterhammer and Frick-Structure interactions and how this can be generalized into metric graphs. And at the end, I'll also mention the fact that we can find long wavelength correction to singularity scattering for acoustic waves. There are perspectives to this work, and for example, there is a project on trying to use this Waterhammer for leak detection into networks. It's just a starting project from the ERNR. And I will end acknowledging my collaborators. Alexandre Ball, who did his PhD mainly on the one pipe problem that I mentioned into the talk. And also contribution of Romain Guibert, will provide all the numerical tools for the geolocalization of waves I mentioned in the beginning. And from that, I thank you very much for your attention. Sorry to be late.
I know that there is no time, but maybe time just for one single question at least. Oh, yeah.
Thank you so much. You pointed out how easy it is to get large Waterhammer pressures, but surely it must make a difference whether you get cavitation or not.
Could, yes, yes.
Do you have any idea what that changes in the formalism?
It's difficult to say how much the cavitation is going to change the pressure amplitudes, but I know that it changed quite a lot, the phenomenology. So but I'm very ignorant of that topic, sorry.
Is there another question, maybe? Ah, Plenty of them. So if you are kind, afterwards you give the microphone.
Yep, so thank you very much. I like the two time scale analysis that you showed. Do you think it could be applicable to other systems where there is a, damping is not obvious? For example, usually you do normal mode analysis, for example, of damped oscillation of droplets or something like that. And there is no closed form for the Laplace transform solution. So, if people have used this type of analysis to derive the typically damping coefficient and the phase shift drift for these systems?
I guess so, because even if you don't have a closed form analytical, you can still solve numerically the leading order, and that might make it possible to find at least numerical things. So now your question is more: do I know that on specific problems with drops or so on? So I don't, but I believe it's possible to do it.
Okay.
Just an intuition.
Okay, thank you for your talk. Just a question on, is it possible to extend this to thermal effects with thermal boundary layers and go to the field of thermoacoustics with this kind of method?
I guess so. I would say the most obvious extension I was thinking about was solid waves, where you have various degree of freedoms of the waves. Like torsion, for example, shear and compression. All those modes are going to be coupled at connections, and I was wondering that in beams problems, for example, that will be a natural extension of this framework. But thermoacoustic could be one. And I know that, for example, for water hammer, there are what is called a thermal water hammer, coming from sudden change in temperature that makes change in the compressibility that then produce waves. That happens. So yes, I guess so. But then you will have to solve an auxiliary problem associated with a thermal problem, probably.
You have questions today.
Thank you for your presentation. Many interesting things for me. My first question is about the coup de bélier or water hammer. I discovered the Bergeron observator when I was working on electrical lines and networks. And it's fun for me to see that it came from hydraulic problem to electrical problems. And I know there has been quite a lot of developments in the electrical network, because of course this water hammer turns into electrical shocks in high voltage lines. So is there any main difference between the thing you presented and the Bergeron observer as it is used in the electrical networks?
Oh, so I'm sorry, I don't know what you call Bergeron operators or what Bergeron observators.
Well, it's very similar to the thing you presented. It's just like saying the initial impulse is going to propagate on the line according to the characteristic impedance of plane waves, and then reflects and so on.
Okay, so well, yes, I guess there is an analogy, but I'm sorry, I don't know what you mentioned about. So
and I had another question, which is related to the acoustic networks.
Yeah.
Because we are working on acoustic networks as musical instruments, where you have a main tube and many side tubes. And do you know of any possible connection between this kind of work?
I guess there is more or less direct applications in that case, and that would be very interesting for me to apply this kind of methodology to real systems. I would be very happy to collaborate. Or for example, the impedance stuff I mentioned at the end, to find them explicitly on given geometry, and then to measure the predictions and to let's say confront the theory with experiments, to my knowledge, has never been done. I mean, these formula are just fresh.
Okay.
Thank you, Franck. Thank you all. And Franck will be in the lab this afternoon. So if you want, just reach out. And for the ones that still want to talk with Franck, we can have lunch together. So thank you, Frank. Bye
Thank
bye.
you very much. Okay.